In this lecture, we'll be starting a new chapter, which is process synchronization. So we will try to understand what is process synchronization, why we need process synchronization, and how it is a very useful and important part of operating systems. So by process synchronization, we mean that we need to have some kind of synchronization between the processes. And why do we need that? We'll find out as we move ahead. So first of all, we need to understand the term cooperating processes. So it says here, a cooperating process is one that can affect or be affected by other processes executing in the system. So we know that there are multiple processes executing in a system. So if the execution of one process can affect other processes and vice versa, then we say that they are cooperating processes. So these cooperating processes can either directly share a logical address space, which is both code and data, or be allowed to share data only through files or messages. So when we are having cooperating processes, they will be sharing a region of data. There will be a shared region of data which these cooperating processes can access and manipulate. So they can either share a logical address space. So by logical address space, we mean that they are sharing both the code and the data, or they will be allowed only to share data through files or messages. So these are the two ways how sharing can take place between cooperating processes. Now, what is the problem here? So the main problem that we have here is concurrent access to shared data may result in data inconsistency. So we know that cooperating processes will be sharing a region of data. So they will be able to access that shared region and will be able to access and manipulate that shared data. Now, if multiple processes are concurrently trying to manipulate data, then that will lead to data inconsistency. So that is the main problem that we have here. If two or more processes are trying to manipulate the same data at the same time, then that will definitely lead to data inconsistency. So that is why we need process synchronization. So in this chapter, we discuss various mechanisms to ensure the orderly execution of cooperating processes that share a logical address space so that data consistency is maintained. So this is what we are mainly going to discuss in this chapter. We are going to discuss various mechanisms that will ensure the orderly execution of cooperating processes that share the logical address space. So when they are sharing a logical address space means they are sharing both the code and the data. So for these kind of processes that are sharing both code and data, when they concurrently try to access shared data, it is going to result in data inconsistency. So we need to discuss about the various mechanisms that we have that will ensure that the cooperating processes will share the logical address space in an orderly fashion such that the data inconsistency can be avoided. And hence we will have consistency maintained in our data. So this is the main thing in this chapter and the main objective that we are going to follow. So keep this in mind that this is why we need process synchronization. Now let's take some examples to understand in a clearer way why this process synchronization is important. So the best example that we can take is the concept of shared memory systems. So in one of our previous lectures, we have already studied about shared memory systems. So in shared memory systems, we saw how multiple processes share a region of memory, and the processes can write into that region of shared memory and also read from that region of shared memory. So there, when we discussed about these shared memory systems, we came across a problem known as a producer-consumer problem. So if we just recall that, we can see that in producer-consumer problem, what was happening was a producer process produces information that is consumed by a consumer process. A producer process is the one that is producing information, and the consumer process is the one that is consuming the information. So we took some examples like a compiler may produce assembly code which is consumed by an assembler. And also we can take another example like a web server is producing web pages, and then the client through the browser is consuming the web pages. So one solution that we found for this producer-consumer problem was the use of shared memory. So we have seen how memory was shared between processes and how multiple processes could write to that region of shared memory and read from the region of shared memory. And also we see that there was something called buffer that we had. So a buffer is a place where the producer will produce the information and keep it, and it is also the place from which the consumer will consume the information. So the buffer will reside in a region of shared memory that is shared by the producer and the consumer processes. So we also saw that the producer can produce one item while the consumer is consuming another item. And also we must make sure that the producer and consumer must be synchronized so that the consumer does not try to consume an item that has not yet been produced. So these are the things that we saw. And when we discussed about the buffer, we also discussed about two kind of buffers, which is the bounded buffer and the unbounded buffer. So unbounded buffer is a buffer that practically places no limit on the size of the buffer. And bounded buffer is the one that assumes a fixed buffer size. So in bounded buffer, the consumer must wait if the buffer is empty, and the producer must also wait if the buffer is full, because we are having a particular fixed size in this bounded buffer. But in unbounded buffer, there is no practical size. So those were the kind of buffers. So this is just a recapitulation of some of the things that we have studied in shared memory systems, because we are going to use this for explaining process synchronization. So now let's say, for example, we are going to use this bounded buffer and we are going to modify it a little bit. So what are some modifications that we are going to make? So we know that in a bounded buffer, we need to keep track of the items that are present in the buffer, because we need to know when the buffer is full and we also need to know when the buffer is empty. So let's say that we are going to use a variable that is going to count the number of items that are present in a buffer. So that means when something is added to the buffer by the producer, the variable will be increased, and when something is consumed from the buffer by the consumer, then the variable will be decreased. So let's say that the name of the variable is counter. So counter is the name of the variable which is going to keep track of the number of items present in the buffer. So for the beginning, we initialize the counter variable to 0. That means the first value is 0. So now what we will do is, the counter is incremented every time we add a new item to the buffer, and the counter is decremented every time we remove one item from the buffer. So whenever a new item is added to the buffer by the producer, then we are going to increment the value of this counter by 1. So we are going to have a counter plus plus operation. That means increment the counter by 1. So counter plus plus is equal to saying counter equal to counter plus 1. So we'll be incrementing it by 1 every time the producer adds an item to the buffer. And similarly, the counter will be decremented every time we remove one item from the buffer. That is, every time an item is consumed by the consumer from the buffer, we will decrement the counter by 1. So we are going to have a counter minus minus operation. So counter minus minus means counter equals to counter minus 1. We are decrementing the value of the counter by 1. So let's take an example based on this. So let's say, for example, suppose that the value of the variable counter is currently 5. So we have a buffer where the counter variable is currently 5. So 5 is the value. And the producer and consumer processes execute the statements counter plus plus and counter minus minus concurrently. So at some point of time, when the counter's value was 5, the producer process and the consumer process both respectively tries to execute the statements counter plus plus and counter minus minus concurrently. That means the producer tries to produce an item and hence it wants to increase the counter by counter plus plus. And then the consumer also at the same time consumes an item and wants to decrease the counter value by counter minus minus. So what will happen in this kind of a scenario? So following the execution of these two statements, the value of the variable counter may be 4, 5 or 6. So if these two statements are executed, then following the way in which these executions took place, the value of the counter variable could be 4, 5 or 6 depending upon how it was executed. So let's say that the counter variable was 5 and then counter minus minus occurred first. Then what will happen? 5 will be decremented by 1, then it could be 4. Or let's say that when counter's value was 5, counter plus plus happened. And then what will happen? The counter's value will be incremented by 1. So 5 plus 1, 6. So among these three values, 4, 5 and 6, which should be the right value of the counter? So actually the only correct result though is counter equal to 5, which is generated correctly if the producer and consumer execute separately. So the actual value or the actual result should be 5. And why is that? That is because the initial value of the counter was 5 And if one item was produced by the producer, then it will become 6. And then if one item was consumed by the consumer, then it will become 6 minus 1, 5, back to 5. So it's just like, let's say that you are having 5 apples with you, and then your friend gave you one more apple. So you got one more apple, it became 6, and let's say that you ate that apple. So how many do you have now? You still have 5. So that is the same thing that should happen here. The original number was 5 and the producer produced one item, but the consumer also consumed one item. So the final value of the counter should be 5. So 5 is the only correct result that should be there. But will we have the correct result of 5 if the producer and the consumer try to concurrently execute counter plus plus and counter minus minus? Let's try to find that out. So before we go into that, we need to understand how does counter plus plus and counter minus minus work in a machine level. So when we are writing a program, we may be writing the code saying counter plus plus or counter minus minus, but we need to have an understanding of basically how does it happen at the machine level. Then we'll be able to understand how these values come. So this is how counter plus plus will be implemented in a machine language. So counter plus plus may be implemented in a machine language on a typical machine as follows. So when we are writing programs, we are writing in some high level programming language, but everything finally it breaks down to the machine language, and that is how it will be executed at the low level. So let's see how it is done. So when we implement the counter plus plus operation, this is what happens. So first of all, we are making use of registers here. So at the machine level, we are going to make use of registers. So here let's say that we have a register called register 1, which is a local CPU register. And what will first happen is the value of the counter will be stored to the register 1. So what is the value of the counter? It is 5. So the value 5 which is in the counter will be stored to register 1. So register 1 now has the value 5. And mind it, counter is still 5, register 1 is also 5. Now what happens is the register 1's value is incremented by 1. So register 1 equal to register 1 plus 1. So at this point of time, what happens? The register's value, the value that was in the register, which was 5, is incremented by 1, which is 5 plus 1 equal to 6. So the value 6 is now stored to register 1. So at this point of time, remember, register 1 holds the value 6 and counter is still 5. Then at the last step, what happens is counter equal to register 1. That means whatever value is in register 1, store it to the variable counter. So what is the value in register 1? It was 6, we just saw it. So the value 6 will be now stored to the counter variable. So the counter now becomes 6. So that is how counter plus plus works using the registers. First, the value is stored to the register from the counter, then the register is incremented by 1, and then the value in the register is stored back to the counter. So that is how counter plus plus works on a machine level. So similarly, counter minus minus may be implemented in machine language on a typical machine as follows. So in a similar way it will be implemented. So let's say we have register called register 2. So the value of counter, which was 5, will be stored to register 2. Then register 2's value will be decremented by 1. Register 2 minus 1. So 5 minus 1 equal to 4. So the value 4 will be now stored to register 2. Then what happens? Counter equal to register 2. That means whatever value is in register 2, store it back to the counter. So the value 4, which is the value of register 2, is stored back to the counter. So counter becomes 4. So that is how counter minus minus is implemented in a machine level. So now since we have a basic understanding of how counter plus plus and counter minus minus are implemented in machine level, now we are in a position to understand this example. So here we said that the counter's current value is 5. Then the producer and consumer both tries to execute counter plus plus and counter minus minus at the same time. So what will happen? The values can be either 4, 5 or 6, but the only correct value should be 5. So let's see what the value will be. So here is a table that depicts how this process takes place. So at time t0, the producer is trying to do its execution. So what is the producer trying to do? The producer wants to produce an item to the buffer, and hence it wants to increment the counter by 1. It wants to do the counter plus plus operation. So what is the first operation that should take place in a counter plus plus at the machine level? First of all, in register 1, the counter's value should be stored. So first of all, at time 0, the producer executes and it sets the value of register 1 equal to the value of the counter. So the value of register 1 is equal to 5 because we are assuming that the present value of counter is 5. Alright, now at time t1, the producer will do its next execution. Now what is the next execution in a counter plus plus operation? The register's value has to be incremented by 1. So register 1 is equal to register 1 plus 1. So the value in register 1 is incremented by 1. So what was the value? It was 5. It is incremented by 1, so it becomes 6. Now let's say that at time t2, the consumer is consuming something from the buffer and hence it also wants to decrement the value of the counter by 1. So what happens? The consumer is now executing and then it wants to do counter minus minus. So what is the first step? Register 2 equal to counter. So it is going to say register 2 is equal to counter. The value in counter should be stored to register 2. So mind you, till here we have not modified the value of counter. The value of counter still is 5. Only the registers have been modified. So when we say register 2 equal to counter, what will happen? Register 2's value will be replaced by the value of the counter. And what is the value of the counter? It is still 5. So register 2 is equal to 5. So what is the next step in counter minus minus? Register 2 equal to register 2 minus 1. So the consumer still does its execution. And what is it? Register 2 equal to register 2 minus 1. So what is the value in register 2? 5. So 5 minus 1, 4. So that is the thing that happens in register 2. Now let us observe and see that till this point, only the registers have been modified by the producer and the consumer. But the value of counter has still not been modified yet. So what happened here, both the producer and consumer are concurrently trying to modify the value of the counter. So that is why they did all these steps till now. Now what happens? If the producer is the first one to get hold of the counter, then it will do its execution and do this final step, which is counter equal to register 1. So if counter equal to register 1 happens, what will be the value of counter? What is register 1? Register 1's final value is 6. So the counter will be stored with the value 6. So counter equal to 6 will be the final value of the counter. But let's say that if the consumer was the first one to get hold of the counter, then what will happen? The consumer will execute this last statement, counter equal to register 2. So if counter equal to register 2 occurs, then what will happen? What was the value of register 2? It is 4. So the counter's value will be stored as 4. So this is what happens. They are trying to concurrently execute, and when they're trying to concurrently execute, whoever is first getting hold of that counter will assign the value to the counter. So if producer is the first one to get hold of the counter, then the counter value becomes 6. And if the consumer gets hold of the counter first, then it is going to store the value of counter as 4. So here we see that we would arrive at this incorrect state because we allowed both processes to manipulate the variable counter concurrently. So we already saw and we already explained that the correct value should actually be 5. So if the present value of counter is 5 and if one value is added and if one value is reduced, that means if the producer put something there and if the consumer consumes something from there, then the final value should still be 5. But here we see that it is going to be either 6 or 4, which are both wrong. So we would arrive this incorrect state. And why did we arrive at this incorrect state? Because we allowed the counter to be manipulated by the producer and the consumer concurrently. If we had allowed one of them to complete and then let the next one to do its work, then we would have not arrived at this wrong situation. So a situation like this, where several processes can access and manipulate the same data concurrently, and the outcome of the execution depends on the particular order in which the access takes place, is called a race condition. So here we saw that in this scenario, when the producer first gets hold of the counter, it was giving it the value 6, and if the consumer was the first one to get, then it was giving it the value 4. So there is a race between the producer and the consumer. Whoever first gets hold of the counter is the one who is going to give the value to it. So this kind of a situation is called a race condition. So several processes are accessing and manipulating the same data, and then the final data will depend upon the order in which the access took place. So here we saw that if producer is the first one, this 6 is going to be the value. If consumer is the first one, then 4 is going to be the value of the counter. So this kind of a situation is called a race condition. So this is an important term that you should remember. So we see here that we have arrived at the wrong result because we have allowed two processes to concurrently access the same data, and these processes were not synchronized between each other. So clearly, we want the resulting changes not to interfere with one another, and hence we need process synchronization. So we don't want this kind of a situation to happen. We don't want two processes or two or more processes trying to access and manipulate the same data and then causing some kind of inconsistency of the data as we saw just now. We want the data to be consistent. So we need the process to be synchronized with each other, and we don't want the resulting changes to interfere with one another. So this is why we need process synchronization. So this is one strong example that we can see in operating system, and we see that we need to definitely avoid this kind of situations. So we are going to study of various techniques that are there in order to avoid this kind of situations. So we'll be seeing such kind of problems related to process synchronization, and we will be seeing what are the various methods that have been formulated in order to avoid this kind of problems. And as a whole, what we want is we want to maintain data consistency. So that is the main objective of process synchronization. So I hope this introduction to process synchronization was clear to you, and I hope you got an idea of what we are trying to study and why we need to study this. So I hope this was clear to you. Thank you for watching, and see you in the next one.